So now we've talked quite a bit about objects that are rotating, they have angular velocity, they might be changing their angular velocity, they might be accelerating in the angular sense. Much like in the linear sense, to get a linear acceleration we needed to apply a force. Here in the rotating sense we also need to apply a force, and in a rotational sense this is going to be called a torque. So a torque is going to depend, one, on the force that is applied, a direction of a force, but it's also going to depend on how far away that force acts from where an object is rotating. So it's going to depend on that position as well. That position I'm going to write as r perpendicular, and I'll talk about that in a second, and then I'm simply going to say that this is going to be the force acting on it. A couple things to note, first of which I'll talk about the units of torque. It's going to be newtons for the force and meters for the distance, so the unit for torque should be a newton meter. And lastly, it is a vector and direction matters. Very typically what we do is we'll say that the counterclockwise direction is going to be positive and the clockwise direction is going to be negative. I know that's counterintuitive, however that tends to be the accepted way to define these things. So talking about this lever arm right here, that's going to be the perpendicular distance from the axis of rotation to the line of action along which a force acts. If we consider this door right here, it's rotating about its hinge. It has two forces that are applied to it at two different distances, so it's going to have two torques acting on it. The line of action along which the force acts in both of these cases is going to be straight up and down, perpendicular to the hinge. So force A is acting along this line right here. The perpendicular distance from the axis of rotation right here to that line in this case is going to be RA, so RA is going to be the lever arm for force A. Similarly, the line of action for force B is going to be straight up and down, also perpendicular to the door, so the lever arm is simply going to be RB. I'll talk about the more complicated cases in a couple of slides. It turns out that we can use this thing called torque to our advantage, essentially writing torque to be equal to the lever arm, the distance, multiplied by a force. If we're trying to break a lug nut loose from a car wheel, we can only apply a certain, very limited amount of force from our scrawny little physicist arms. However, we can play games with this lever arm distance right here to generate larger or smaller torques. Obviously, if you get a pair of pliers and try to turn this lug nut, it's probably not going to move, but we can increase the torque applied to this lug nut simply by getting a longer wrench. If that still doesn't generate enough torque to break that lug nut free, we get a pipe. We stick that on the wrench. We increase our distance. We can't change anything about a force, but we can produce larger and larger torques to help rotate an object. So let's take a closer look at these things that are called lever arms. Here we have a door on a hinge. It's always going to have an axis of rotation about the hinge. And we've talked about the case of force A, which has a line of action straight up and down through the door here. So it's going to have a lever arm going out to that distance RA. If we consider force C for a second, the line of action of force C is along this line right here. And the lever arm is going to be the line from the axis of rotation right here to where it intersects intersects perpendicularly to the line of action along FC. So for force C, this distance RC right here is going to be our lever arm, and you can see that that's a much smaller distance than RA, and you know kind of intuitively that if you shove a door from the side, as with force C right here, it's going to produce less torque on the door. It's not going to shut it as efficiently. Considering lastly the case of force D right here, the line of action for force D goes along this line right here, and you can see it goes directly through the axis of rotation. So the lever arm for force D must be equal to 0. Force D will produce no torque on this door hinge. And you know, if you shove a door directly towards this hinge, it's not going to swing open or closed. We can take a look at example 8.8 for a quick calculation of torque, defining torque to be the axis of rotation, r perpendicular, multiplied by the force. If the arm is, so here we have an arm with an axis of axis at the elbow, and your bicep is applying some force to that guy that is 0.05 meters away, we can go ahead and we can calculate the torque of that guy to be r perpendicular multiplied by the force, and we're going to come up with 35 Newton meters. If we consider the arm to be bent at 30 degrees here, obviously this r perpendicular distance is going to get shorter, and r perpendicular is going to turn out to be 0.05 multiplied by the sine of 60 degrees. So the torque in this case is going to be 0.05 multiplied by the sine of 60 degrees multiplied by the force of 700 newtons, and the torque is going to end up to be 30 Newton meters. So the key to solving these torque problems is to be able to identify this axis of rotation and be able to say that the torque is equal to the axis of rotation multiplied by the force, where to find the axis of rotation we look at the line of action along which the force acts, and then find the line that is perpendicular that goes through the pivot point, and we have a triangle with r perpendicular on this side and the distance r on this side. Knowing that the angle that it makes, we can go ahead and we can calculate out what r perpendicular is. Simple trig. However, I personally find this to be a very confusing method to calculate torques. What I tend to do is I tend to say, okay, I have a force acting on this door. I'm going to break this force up into two components, the perpendicular component and the parallel component. Now, I know that this parallel component is going to have a axis of rotation of 0. It's going to go directly through the door. This perpendicular force is not going to apply a torque to the door. The parallel force is not going to apply a force to the door. This perpendicular force is going to apply a torque to the door, and the axis of rotation, or the lever arm, is always going to be the radius, or the distance right here. So rather than writing torque is equal to the perpendicular, r perpendicular multiplied by the f, you can also write it to be the distance at which the force is applied multiplied by only the perpendicular component of the force. Either one of these two methods is fine. Use whichever one makes the most sense to you personally. So what we want to do is we want to take these torques and relate them back to accelerations, much like we write Newton's second law for linear motion. We want to be able to do that for rotating objects. And we know that if we have a single point source, then we could write that the force applied to it is equal to the mass times the acceleration. If we take Newton's second law there and we multiply both sides by radius, we're going to get a torque on this side. And if we convert this acceleration to angular acceleration, or angular acceleration multiplied by radius, we're going to get that for a point object that the torque is equal to mass radius squared multiplied by the angular acceleration. This is for a single point mass. If we wrote this for an extended object, what we're going to be doing is we're going to be summing up all of those tiny little masses and those tiny little distances of an object. So we're going to write Newton's second law to be the sum of the torques is going to be equal to the sums of the mass times radius multiplied by the angular acceleration. If I go ahead and I call this a different type of mass, I'm going to call it the rotational mass and talk about it on the next slide. I'm going to write Newton's second law, the sum of the torques is equal to the rotational mass multiplied by the acceleration. So if I know all of the torques that are acting on an object, then I'm going to sum all of those guys up. I'm going to say that must be equal to its rotational mass, which is related to its mass multiplied and how the mass is distributed, and the angular acceleration. So very important equation to know. So this quantity I defined on the last page that I said was the rotational mass is going to be the sum of all the tiny little masses that an object has multiplied by their radius. It has a special name, it's called rotational inertia. You'll also see it referred to as the rotational mass of an object. And again, it's related to the mass of an object as well as how the mass is distributed. So if we have two objects right here and they each have equal mass, this object here has mass that is distributed out to much larger radiuses. What that means is that it's going to have a greater rotational mass. It's going to have greater rotational inertia. It's going to be harder to spin this body to some acceleration than it is going to be to spin this body up to some acceleration. The reason is because this body up here has a much larger rotational inertia because some of the mass is located out at larger and larger and larger radiuses when compared to this guy right here. Now this is a very important slide. What we're looking at here is we're looking at the rotational inertia, this quantity I, for a whole bunch of different objects. Thin hoop with radius r, thin hoop with some thickness, solid cylinder, so on and so forth. So if you see a problem and it says you have a solid cylinder that is rotating with velocity v, what you need to do is you need to go look at this table, figure out which of these objects fit your problem, and you have your rotational inertia. One thing to keep in mind is it's going to depend on the axis of rotation. Looking at this long uniform rod, if it's being spun about the center of it, then you kind of know intuitively that it's going to be easier to spin than if you spin it around through the end. So this one is going to have a larger rotational mass than the other one. So it depends not only on the mass, the radius, the length, etc., but also where it's being, where the axis of rotation is. I just want to go back and highlight this very quickly because it's part of one of the problems that I worked. If we look at this quantity for a whole bunch of point masses, the sum of the masses multiplied by their radius, I can take objects that I know, for example this solid cylinder, and add masses to them. If I added a point mass right out here, what I'm essentially doing is I'm going to say my rotational inertia is going to be the sum of the masses multiplied by their radiuses. I'm going to break this up into two different sums. I'm going to break this up into the sum of the masses and radiuses squared here of my disk, in addition to the sum of the masses and radiuses. And in this case, this is going to be my point mass. I can go ahead and I can look this guy up in my table. So 1/2 mass r squared. Add to that my single point mass at a radius r. Now I have my rotational inertia for something slightly more complicated than the cylinder, but since I understand how rotational inertia is defined, I'm able to add point masses.